everyone, welcome to chapter 5. This is a chapter that's can be fun if you let it. It's about energy and changes in energy, and we're going to be looking at the different forms that energy takes, the changes that happen during chemical reactions, and then look at some units of energy and how we can convert between those. So energy is defined as the capacity to do work or to transfer heat. So we have two forms that we can use in our calculations. All of them are either kinetic or potential. Okay, kinetic energy or potential energy. Now, get that underlined. Okay, so kinetic energy is what we think of as energy in motion. So that's energy that we are using, okay, that's being used. Whereas potential energy is that which is stored, that is ready to be used when we need it. And so you can do calculations. We're not going to do calculations with kinetic energy, but it is based on mass and velocity, so because it's moving. So the speed is something that we do look at when we're checking those. One form of kinetic energy that we are going to be looking at in this chapter is thermal energy. Okay, and thermal energy is the energy that's associated with random motion. Okay, so motion of atoms and molecules. So that's why it's kinetic. We can monitor changes in thermal energy by looking at temperature changes. Okay, it's hard to concretely measure the energy, but we can measure changes in the energy, and so that's what we typically do when we're looking at thermochemistry. As I said, potential energy is what's possessed by virtue of its position, okay, and in chemical energy we typically store energy in bonds, okay, and so within that chemical substance we have the potential to do work or to transfer heat that is strictly in those bonds in a chemical. Electrostatic is the other type of potential energy, and that's by position. Okay, so electrostatic energy is based on charges, and if you recall, opposites attract. Okay, and so if they're opposite in charge, they attract each other. If they're the same charge, they will repel each other, just like a magnet, if you've ever seen a magnet. And electrostatic potential is proportional to a couple of things: the distance between the two charges and then the product of the charges. Now, we're not going to be looking at electrostatic, but you do need to know what it is, since it is a type of potential energy that's used in science. Kinetic and potential energy are what we call interconvertible. What does that mean? Okay, so it means that we can convert one to the other. All right, so in chemistry, in a chemical reaction, we can give off heat, which will convert chemical energy to thermal energy. One is potential, one is kinetic. One thing to keep in mind is that the total amount of energy in the universe is constant. So we can't create or destroy energy, but we can change the forms that it is in, just like we saw in the law of conservation of matter. This is the law of conservation of energy. When we're looking at a system, the system is what we are studying, okay? So if we're doing something in a beaker, the system is what's inside that beaker. And then anything outside are the surroundings, okay? And then the total of the system and the surroundings is the entire universe. So heat is the transfer of thermal energy between two objects that are of different temperatures, and so we can flow heat, we can absorb heat, and we can release heat depending on what's going on in that process. So thermo, which stands for heat, chemistry is how we study the transfer of that thermal energy in our chemical reactions. So energy reactions can either be exothermic in nature or endothermic in nature. If it's exo, heat is exiting the system, okay? And so you're seeing the heat exiting the system, which was what was in our beaker. That's going to be exothermic. Now just remember exit, okay? An endothermic process is the opposite, and it's not nearly as intuitive. Energy is absorbed in an endothermic reaction. And it doesn't necessarily have to be heat. It could be other forms of energy that you put in to the reaction in order for it to go. So in the case of an endothermic reaction, such as the decomposition of mercuric oxide, I have to put something in. I either have to heat it up or do something in order for it to decompose into mercury and oxygen. So that's what an endothermic reaction is. I'm putting energy into that system. We're going to talk about several different units of energy. The main one is the joule, or the kilojoule, which of course is going to be 1,000 joules, just like a kilo of anything. And so we already saw that the kinetic energy formula I showed you a minute ago. The other terms that can come from that are derived from that initial kinetic energy formula. A joule is also equal to 1 Newton meter. That's when the force of 1 Newton is applied in order to push something the distance of 1 meter. A Newton is also defined as 1 kilogram times meters per second squared. Okay, now these we use a lot more in physics because they're like real world. I'm pushing stuff around. Joules, kilojoules, you're going to see more in chemistry. One other unit that you may be familiar with is the calorie. So how many calories is in that breakfast bar or whatever? Okay, when we're talking about calories in nutrition, we're really talking about kilocalories. Okay, a kilocalorie, notice it has a capital C. So, and you have to really watch sometimes to make sure whether it's a capital C or a lowercase c, because the lowercase c is the calorie, and 1 calorie is equal to 4.184 joules. Kilocalorie is 1,000 calories, and 1 calorie then is 4,184 joules. So let's work a problem and try to do these conversions, because we're not going to do the kinetic energy stuff. Calculate the number of calories in 874.1 joules. Now, I've given you some conversion factors that you can use to do this. And so I'm going to start with this because this is a measurement. 874.1 joules, and I want to convert that to calories. Notice it's lowercase c, so calories. So 8.741, and I gave you a conversion. And remember, in dimensional analysis, I'm going to write joules down there because I got to get rid of it because that's not what I'm looking for. I'm looking for calories. So 8.874.1 joules there are in 1 calorie, they're going to be 4.184 joules. Okay, and so I just simply do the math. It's pretty simple in this case. Joules will cancel. It will leave me with calories, and you should get 208.9 calories. So it's just important that you can do those conversions, because some of the problems that you will use are going to need you to convert from one to the other. All right, now in a nutrition label, it tells us that 1 tablespoon of food, whatever it is, has 130 calories. Okay, that's the big C. How many joules of energy is provided in a single serving? So we're looking at 1 tablespoon. It has 130 big C calories, which we know, I've already told you, is kilocalorie, right? So there are 1,000 little c calories in 1 big calorie, okay? Because 1 big calorie equals 1 kilocalorie. So that gets rid of the big C calories, and I've got little c calories left. Then I can easily get from calories to joules, because I know that there are 4.184 joules in 1 calorie. And then I simply do the math. That will give me 5.4 times 10 to the 5th joules, or 543, if we're not too worried about significant figures, of kilojoules. Okay, so my joule answer is got the correct significant figures. So that's all there is in this introduction to thermochemistry. We're going to look at changes in the system in the next module of thermochemistry in part 2.